Hey guys, so obviously, as you know, as I told you yesterday or whatever, we have a sub today. So this is the video lecture for today. I'll go ahead and share my screen here so I can get to what I want. Let's share. All right, we should be good to go now. So kind of picking up, and these were this kind of packet of notes here. I had sent this to you guys the last time I had a sub, and it is posted on Schoology, and make sure you guys peruse through Schoology. Look at the upcoming schedule that's posted there. So these are some notes we started a little while back. We talked about, why do we organize the periodic table? For the purpose of placing materials or different elements, within groups of similarities, right? So these vertical columns are groups, the rows are called periods, and these vertical columns that are groups have similar properties, right? And just so you guys know, like the reason why I'm looking this way is kind of looking at my second monitor here. So 1, 2, 13, 14, 15, 16, 17, 18 are the main group elements, and that center region that's kind of dropped down are called the transition metals. So one of the things we talked about, kind of special names for different groups, 1, 2, 17, and 18. The one that I wanted to kind of highlight here with just for at least a few minutes here, my plan was today was to actually do this live with you guys, a demo, but the way it is, it's the way it goes. So what I have is I got just kind of a quick little video clip to kind of show you guys that I'll move over here that shows this same reaction that I was going to be showing anyway.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Zoom in real quick. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's been freshly cut, and you can see the dullness to the other sides.
Okay, so we got lithium, sodium, and potassium, these three elements that are group 1 elements within group 1. They're in the same column. These are metals, right? They look metallic, but they're really soft. The word that's used is they're called sectile, S-E-C-T-I-L-E. This teacher here, he can cut them with a knife. That's what the exact same thing I would have been doing. But I've been standing in front of you guys today doing this in front of you. And these group 1 elements, just so you guys understand, as a metallic substance, as an elemental substance with an S1 electron configuration, these types of elements really won't occur naturally. You'll notice on the paper toweling, it's all like kind of looking oily. These are all elements that are made in a lab. You buy them. They're sitting in or stored in oil, like mineral oil, for the purpose that they react vigorously with water, and they can react with the water, the humidity in the water that's even in the air in the room. Ultimately, what he's going to do is he's going to take these lithium, sodium, and potassium samples and drop them into some water. And if you remember, right, we talked about these react vigorously with water. They'll break the water apart to produce hydrogen gas and oxygen gas, right? And sometimes enough that it will even ignite that hydrogen gas that it's producing, because these group 1 elements have an S1 electron configuration. They got like 1 extra electron. They will readily lose that electron to achieve that of the previous noble gas. All right, so let's take a peek at the video real quick here. I'm gonna kind of skip ahead a little bit.
Generate hydrogen gas in lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off there. Okay. So
he drops some lithium in. The lithium it's fuzzing, bubbling, fizzing, bubbling, producing some of that hydrogen oxygen gas. The pink colors because phenolphthalein is added to the water. It's an acid base indicator. Remember, these are called the alkali earth metals. Alkali means basic, okay? And as these elements lose their electrons, and as they're removing hydrogen from the water, it causes the solution to become sort of more and more basic. So the pink color is due to the removal of hydrogen gas in this reaction. But the lithium, kind of the first in this column, right, is sort of the least reactive.
Maybe a little bit of liquid water. But it's not as reactive as, say, sodium. So I'm going to put sodium in the next one. Sodium is actually probably going.
So the sodium here that's been added, a little bit more reactive.
There's some sparks, there's some shrapnel.
A couple little sparks, a couple of things flying out, but more reactive than the first. So this is sodium in the second beaker, a little bit more reactive. Now I'm going to kind of push ahead here to potassium, the last one.
In terms of amount, you'll find that the reactivity is a little bit greater.
So the potassium right away loses those electrons so readily. It's so energetic. This is, you know, an S1 electron configuration, 3s1, 4s1 electron configuration. So remember, higher energy, principal energy level, more energy being lost as these electrons are being dropped out, creating, in this case, potassium ions. And you saw the sparks in the flame and the kind of the greater reaction. All three of these have similar reactions, similar results, but the energy increases as you go down in the reaction, that column in the group 1 elements. Okay. All right, then moving onward. So similar properties, and again, these similar properties just demonstrated by this little video clip is due to the electron configurations of those elements. Now, I believe this is kind of where we left off when we were talking. So this stairway deal, right? The idea of metals versus non-metals. So the periodic table has kind of embedded within it this sort of what I call a stairway. And I'm going to go to another screen here. Okay. And this stairway, see, and what I'd recommend you guys doing, have out one of your periodic tables and draw in this stairway, darken in this line. And even on the photocopies of the periodic tables that you guys have gotten, it is darkened in, it's there, it's just not very heavily lined. But this line recognizes or separates the metals, which are in red, and the non-metals in blue, on the metals on the left side, non-metals on the right side. And then you'll notice kind of right along the border, got a bunch of these things that are called metalloids, right? So metals have certain characteristics, non-metals have certain characteristics, and metalloids, or this, or sometimes called the semi-metals, have characteristics that are shared between the two. Like for instance, silicon. So silicon is used in like microchips, computer chips, different electronic devices. Silicon is a metalloid. It doesn't really look like a metal. It kind of looks almost kind of like gray plastic in a way. But it is one of the best conductors of electricity. So it conducts electricity very well, like the metals do. So this stairway is important for us to know that separation, because as we get into talking about naming the ionic compounds and recognizing them, and naming and recognizing binary molecular compounds in these next couple of days, knowing that sort of distinction is going to be big, because the metals is going to be a giveaway for a certain type of compound. So this stairway is also depicted on page 36 in your book in figure 2.7, just so you guys know if you want to flip that open. Okay. So metals versus non-metals. Metals have a characteristic that's called luster, which is basically like a shine. You know, you look at a metal, you look at a shiny penny, you look at a shiny nickel, whatever, it's good. You can tell that it's metallic, right? Metals are malleable, which means that you can bend them into certain shapes. They will bend and hold that shape, twist them into a wire, all those sort of things. And then metals will also have a high electrical conductivity. Most metals are pretty good at conducting electricity. Now it's kind of interesting, like and now it's not necessarily true with all metals, right? So again, another example here, aluminum along this sort of stairway, right? Aluminum is a metal, but it's not particularly good at conducting electricity, right? It's a low electrical conductivity, but it's right along that stairway, right? Even though it's not a metalloid, I mean, it is considered a metal, but it's not, it's right along that stairway. in the fact that while it's a metal, it doesn't necessarily have great conductivity. It shares sort of these properties of these two different sides of that borderline on this chart, okay? And then the non-metals obviously do not show metallic properties, and it's kind of maybe a sort of a redundant statement, but does not show the properties. And then again, metalloids are an intermediate, okay, along that line. Again, figure 2.7 lists those, right? And then we just talked about some of these intermediates like that of like silicon is a great example, showing both of those properties, okay? All right. Just as a note on your own time, guys, make sure you read pages 35 through 47 in your books. Not going to necessarily pause to do that right now. And then page 38, just as sort of a brief little note here, right? You know, what are the biologically important elements? CHNOPS, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. They compose 97.5% of all living materials. So CHNOPS, or if you rewrote this, SPONCH, sponge is another way to remember. These 5 elements compose 97.5, nearly all of living materials. Earth's crust is made out of silicon and oxygen primarily, right? So the rocky portion of Earth's crust. You know, why do I mention this? You know, I mention this again to sort of develop this level of comfort. You know, we're talking about all these elements in the periodic table, yeah. You know, we got 118 of them all over the place, right? But when you kind of start to boil things down, and it's about understanding trends, it's about not necessarily understanding everything there is to know about every element, but what these different elements are in terms of what group do they appear in, what section of the periodic table they appear in. And, you know, when we boil it down in a lot of ways, when we talk about, you know, a lot of the materials that we encounter that we as living things are made up of, you know, it's maybe 6, 7, 8, maybe it's, you know, 10 to maybe upwards of only maybe at most about 20 elements make up just about everything there is around us, right? These other elements that are on the periodic table are in trace amounts and are quite less common. So as we develop an understanding, you're going to see these trends with just sort of interactions of kind of the big maybe 10 or 20 elements, and that's it. And we can get used to that as we can kind of, you know, as you guys continue as chemistry students, okay? All right, now, just kind of a quick little note here, molecules versus ions. So in nature, isolated atoms really are very rare. When we talk about the periodic table as these sort of elemental forms of substances or of elements, and we think about them as isolated atoms, it's actually pretty rare. And as demonstrated, you know, the video that we just watched, right? Group 1 elements, they don't want to exist as those elemental form with that extra electron. They get rid of that electron and they become +1 ions. So lithium and sodium and potassium will become +1 ions. You know, the noble gases are really kind of the only exception to this rule. And why are they the exception? They're the exception because they already have a p6 electron configuration. They have all the electrons they want, so they're not going to gain, lose, or share, right? Atoms can combine with each other, and they will form molecules when atoms combine with each other and those electrons that are being shared, okay? Atoms will combine with each other as ions when an atom has either gained or lost electrons, and they will form ionic compounds. So molecules and ions really are the building blocks of all things around us, within us, okay? So a molecule, okay, kind of said, is 2 or more atoms combined to form an uncharged molecule. Usually both or all of the elements or atoms involved are non-metals. This is kind of an important piece, okay? A side note, if the compound or the formula involves a metallic element, that points you to it being an ionic compound. I'll have some more things to say about this later, right? Molecules are held together by covalent bonds, which means they're shared pairs of electrons. Covalent bonds are shared pairs of electrons. It's another way to accomplish an electron configuration of a noble gas. And we'll end up exploring more on this later as we get into second semester. Covalent bonds are generally pretty strong, okay? These covalent bonds that are in shared molecule or that are shared between atoms and molecules are generally pretty strong. There are intermolecular forces between molecules that are usually pretty weak. A great example of this are like hydrogen bonding between water molecules. So water molecules, like H2O, so HOH, okay. There's slightly charged areas on a water molecule where the hydrogens become slightly positive and the oxygen atoms of other water molecules will become slightly negative, okay. And what happens is a weak attraction between different, between hydrogen atoms and oxygen atoms within water. This is why, like when water, when you fill up a graduate cylinder, the water kind of sticks to the side. So if you fill up a glass of water, it kind of like bubbles up. It doesn't spill out, it bubbles up because of those weak intermolecular forces or interactions between atoms of molecules, okay? Now, molecular formulas, and we've talked molecular formulas, empirical formulas. Molecular formulas really tell us the number of atoms with the subscripts. Sorry, this typo there, subscripts. Okay, so I got kind of 3 examples. So these are molecular compounds. They're containing all non-metal elements. Okay, these are all non-metallic elements. And I do want to, I should have said this when we were looking at this image, just to notice that hydrogen is a non-metal, but it's listed over here, okay, on the periodic table. Remember, hydrogen's, it's kind of unique. It only has that s orbital. So it behaves kind of like a group 1 element, but it really behaves more as a non-metal. So it's sort of, you could almost kind of fit it in 2 spots, here or here. But like I said, generally it's placed over here because it fits in that S1 electron configuration, okay? Sorry, I should have said that earlier. So molecular formulas are just showing the number of atoms, what atoms are in the compound, and a molecular formula is the true formula, the true number of atoms within that formula. We've talked about comparing molecular and empirical formulas, and I'll get back to that in a little bit. Structural formulas are these, right? These little sort of structural formulas that I've drawn out, you've probably seen before. The dashes represent shared pairs of electrons. The dots represent unshared pairs of electrons, and structural formulas show the pattern of how the atoms are oriented within the molecule. Now, don't get too caught up in this. We're gonna practice this and how to draw these and do these and all the kind of how to construct these as we get into second semester. But I'm doing this as sort of the lead up to these discussions over the next couple of days. You'll notice, and I kind of highlighted here, and this isn't 100%, but for the most part in molecular formulas, the first atom listed is usually going to be the central atom in the molecule or in the structural formula, okay? It's not necessarily true all the time. You see H2O, it's kind of an exception to the rule, but the central atom is usually the first one listed and is going to be the central atom within the structural formula that is produced, okay? And then last, there are these things called condensed structural formulas. So this is a condensed structural formula, right? And you remember back when we had the balancing chemical equations worksheets, we had a few that were written out like this, and I pointed them out. I said, these are kind of funky, aren't they, guys? It said like CH3, CH2, 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 CH3, like it repeated. It was like, why didn't they just write down C4H10, whatever, right? This is the reason why. It was a condensed structural formula. It gives you a clue, and think of it as an intermediate. It's an intermediate between a molecular formula and a structural formula. They write it out so that it gives a clue as to the structure of the compound. Because if you wrote out this formula as like CH4O, you wouldn't necessarily know that it's an alcohol and it has this sort of construction. So there's a CH3 grouping right here. There's the CH3 grouping. There's an OH kind of tagged on the end, and there's that OH tagged on the end in the full structural formula that I've drawn right off here to the right. So this OH is a tag of what are called functional groups. If you see an OH ending on a condensed structural formula, that says that it's, or tags it as an alcohol, right? Here's another example, maybe a little bit more obscure, but the same idea. There's the CH3, and there's the NH2. there's the CH3 area of the molecule in the full structural formula, and there's the NH2 grouping, right? So this tags it as a group of compounds that are called amines, okay? So there's all kinds of different amines, methylamine, and methylamine, but these are all functional groups that tag it as belonging to a class of compounds. So by writing the formula like this, it's not so funky. It's just a way of communicating in chemistry that says, hey, I'm an alcohol, or I'm this, or I'm that, okay? So you'll see that with these condensed structural formulas as we, again, kind of continue through the year. All right. Now, into the real big task at hand, guys. Ions gain or lose electrons. So yesterday I gave you the common ion sheet, and then I gave you the worksheet on naming ionic compounds. You need to make sure you have those two items out as we kind of continue this video. So ions gain or lose electrons. Atoms will lose or gain electrons to achieve an electron stability by achieving a noble gas electron configuration. If they gain electrons, they will become what are called anions, and they obtain a negative charge. Makes sense. Electrons have a negative charge. If an atom loses electrons, they will become positive, right? By losing an electron, okay, they become positively charged because now they've lost a negatively charged particle. It affects the balance within the atom. Then they are known as cations. So cations are positive, anions are negative. My dumb way of remembering it is I had a pet cat named Midnight growing up, and I have positive memories about my pet cat that me and my brothers had growing up when we were kids. So positive cat memories, right? Dumb way to remember things. I know Mr. P's full of them, right? Now, there are kind of two types of ions. There are monatomic ions, and monatomic comes from mono. Mono means one. So it's derived from a single atom. They can be positive or negative. If they are positive, they don't have any kind of special name. We just say sodium, potassium, calcium, whatever. And if you look on your common ion sheet, the +1 ions, like a +2 ions that are on that sheet, you'll notice that then the metal is named. It is what it is. Okay. If it's a monatomic anion though, and this is kind of weird, right? Then the monatomic anions will typically have an IDE ending. So if you look at like the -1 or -2 ions on your common ion sheet, like group 17 has fluorine, chlorine, bromine on it, okay? But as a -1 ion, fluorine becomes fluoride, bromine becomes bromide, chlorine becomes chloride. So that IDE ending is sort of a clue that you're talking about an ion or an ionic compound. Okay. Polyatomic ions, like if you have a polygon, it's a many-sided geometric figure. So polyatomic ions means that they contain 2 or more atoms. And in some ways, I want you to think of this like a charged molecule. And I'll show you kind of more about what I mean by that in just a second. They can be positive or negative as well. There is one positive polyatomic ion that I'm going to make you responsible for that has the special name, and that's the ammonium ion, right? Which is NH4 + 1. Okay. And as you guys look on your common ion sheet, you'll see it says like the section that says selected polyatomic ions. The only positive one listed on there is the ammonium ion. So this is the one that's kind of, you got to look out for a little bit. And again, I'll kind of share with you why that is in a second. But nonetheless, it has its own sort of special name. But again, in the polyatomic ions list, so the selected polyatomic ions, ATE endings and ITE endings in the name. So SO4 -2, that's sulfate, ATE, okay, as an example. Carbonate, CO3, these are ATE endings. So eights and eights. I always kind of say this, eights and eights are a dead giveaway that you're talking about a polyatomic ion and or an ionic compound. And again, this will make a little bit more sense as we get into the actual naming and identifying these, right? All right, so here's a few examples, right? Just to kind of help you guys understand, right? So hydroxide is a polyatomic ion. It's OH -1, okay? To give you an idea, so remember I talked about, think of these as really a charged molecule, right? So we've got an oxygen sharing electrons with hydrogen, but overall, within its collective structure, it has gained one extra electron to give it that -1 charge. There's the ammonium ion that I just mentioned, a few, NH4+1. It's a charged molecule where we have no nitrogen, central atom, 4 hydrogens sharing electrons with it. But overall, within its collective structure, it has lost 1 electron, giving it the +1 charge. There's the sulfate anion that I just talked about. There's the SO4-2, the sulfate anion, ATE ending. Sulfur, 4 oxygen shared electrons among this, but overall in its collective structure, it has gained 2 extra electrons to give it a -2 charge, okay? So covalently bonded, think of them as sort of covalently bonded molecular compounds, but they've obtained an overall charge within the collective structure of that molecule, which is why they're polyatomic ions, okay? All right, now we're on the home stretch, guys, okay? So ionic compounds are electrically neutral, okay? In other words, if I combine this common ionic substance, sodium chloride, which is salt, if I combine sodium, right, with chloride ions from, say, aqueous solutions, they will form, right, an electrically neutral compound. The positive and the negative will offset one another within the formula for the compound that it forms. Ionic bonds are quote unquote strong, okay? They're not super duper strong. They can be dissolved a lot of times in water. I mean, we know that sodium chloride, is a fairly resilient solid, but you put sodium chloride, salt in water, it'll dissolve really easily, okay? It is the result of an electrical force between oppositely charged particles. An ionic compound or an ionic bond, sorry, is the result of an electrical force, these oppositely charged particles combining to form a bond between one another, okay? All right, I forgot my balloon demo, okay? So give me a second, guys. Okay. So we've all done this before, right? So simple old balloon. And while this isn't obviously an example of ionic bonding, okay, but we've all done this before, right? Catch the balloon on your hair and you've got static electricity, right? What we've done is we've taken and moved electrons, created static electricity that are negatively charged, and the positive charge of my hair or my shirt here, it sticks to my shirt, okay? The positive charge of the material within my shirt and the negatively charged of the electrons, they stick to one another. We form this sort of slight attraction between them when we do this, right? So we've all done that with a balloon before. We've experienced static electricity. It's not a bad sort of analogy to help understand the opposite charge that takes place within ionic compounds, okay? Now, in addition, sodium chloride and calcium carbonate, right? Sorry, I think I got them right here. And apologize that. So these are ionic compounds that are pretty typical of one another. Here's sodium chloride. Ooh, okay. So it's kind of square in shape, but it looks like kind of like a block of salt. Okay. So that's NaCl. Here's calcium carbonate. Okay, it looks kind of similar, but it's got kind of this rhombohedral shape. Okay, but same idea. These ions will form these compounds. Okay, and the ions will bond at certain angles and create sort of this structure and form. Ionic compounds are typically crystalline solids like this, okay? And we'll get a chance when we get into the percent yield lab later, working with copper sulfate, which is a blue crystalline solid that looks kind of similar to this, but blue in color, okay? All right, so some characteristics of ionic compounds, typically solid at room temperature. The two that I just held up in front of you, room temperature, they're solid, okay? They have relatively high melting points. You know, if I took salt or any of these ionic compounds, I'd have to heat them up to some pretty serious temperatures to get them to melt down. But they will dissolve easily, typically in solution. Okay, as a solid, right? They will not conduct electricity very well, but when you dissolve them in a solution, especially because water breaks into separate ions and will break apart and dissolve ionic compounds into their separate ions. So sodium chloride, solid sodium chloride will break back down. I'll make this just go to this other screen here. The solid sodium chloride will break back down into sodium and chloride ions in a solution. So if I take solid sodium chloride and I dissolve it in water, it'll break back down into its separate ions, okay? So when you dissolve ionic compounds into solution, they become great conductors of electricity, okay? So they have some varying characteristics depending on which form that they're in. All right, now, okay, let's get to the task at hand and then ultimately the homework that you guys got to work on, the worksheet, okay? So talking about writing and naming formulas for ionic compounds, and also really ultimately recognizing formulas for ionic compounds, okay? First note, anytime that you write down a formula for an ionic compound, it must be an empirical formula. So all formulas for ionic compounds will be empirical formulas, which means that they're the simplest formula, okay? The total charge of the two opposing ions, okay, must equal 0. Right? In the first position in the name, it will be a positive metal element. And like we said before, typically you just name it. So like sodium chloride, it's just, you just name sodium, right? It doesn't have any special name. Now we've mentioned there's the ammonium exception. That's the only positive polyatomic ion that will appear in the first position in the name. The second position in the formula. So again, so let's just stay with this example of sodium chloride that we're kind of riding with here. Sodium is a metal. It's in that first position. We just say sodium, okay? In the second position, we've got chlorine, right? And that's a non-metal. So chlorine is a non-metal, right? Chlorine's over here. Sodium's over here. It's a metal in the red section. Chlorine's in the blue section, okay? So back to my screen. It has a special name. So it's not sodium chlorine, it's sodium chlorine becomes chloride, right? And you'll see this in your common ion sheet as you guys are going to start to work to assemble these, okay? All right, so some examples. So there's that. So this would be called sodium chloride, okay? Now I'm giving you the name of a compound. That's what you're gonna be doing on your worksheet, guys. I've got one side is like, it gives you just the formula and you're gonna write down the name. And the other side gives you the name and you're gonna write down the formula. So this next one is calcium chloride, okay? So that would be, I'm gonna take Ca and that's +2, okay? And then chloride is -1. Okay. Now, when I say crisscross method, what do I mean by that? When we're writing these formulas for ionic compounds, the charge will give you the key to the subscript for the opposite element. Okay. Now, the sign on the charge doesn't get carried, but the absolute value of this number is what's going to get carried to your subscript. So this would, calcium chloride would be Ca Cl2. I don't write the 1, but then I write the 2 over there for my subscript. So the formula for calcium chloride is CaCl2. CaCl2. Okay. MgS, magnesium. S, what is that on the common ion sheet? It's not sulfur, it would be magnesium sulfide. F-I-D-E, I-D-E ending, right? IDE ending is a dead giveaway that it is a ionic compound. Okay. Iron 3 nitride. You'll notice on your common ion sheet, there are some elements that are listed that have Roman numerals next to it. That's why I put this example in there. These Roman numerals signify something. They signify the charge of that ion. Iron happens to come in, they're a transition metal, right? Back to this. Oops, sorry. Remember, these transition metals are, these transition metals are this sort of drop down area that's 3 through 12, and iron is sort of smack dab in the middle of it. Iron has multiple forms. There's like iron 2 and iron 3. The Roman numeral designates which charged form it is. And we'll talk later about why they do this, why these different transition metals will act like this. It has to do with electron configurations. Surprise, surprise. But nonetheless, the Roman numeral is a dead giveaway. So iron 3 nitride. Iron 3 would be Fe plus 3. Okay. Nitride, that's nitrogen. So nitride is N minus 3. Okay. Crisscross method. Some of you are probably thinking, should I write this down as Fe3N3? The answer is no, because if the charges are equal and opposite to one another, you can just smash it together. It's just Fen. And why is that? Goes back to what we said. If you're going to write down the formula for an ion compound, it must be an empirical formula. So when in doubt, if you ever write something down, if you can simplify your subscripts, then you need to do it. Okay. Aluminum chromate. Gosh, sorry, I forgot my common ion sheet. I'll be right back. Can't remember what the charge and formula for chromate is, so I got to get my common ion sheet to do this, right? So aluminum has a charge of +3, so aluminum +3, and then chromate is CrO4 -2, CrO4 -2. Okay. I'm going to erase and clean some of this up here so I can make a little more room here. Okay. Crisscross method, right? Boom. That's your subscript. Charge becomes, the absolute value becomes your subscript. And now we write down Al2, and then I want you to notice something, CrO4. I've got a polyatomic ion, and I've got to use a subscript next to it. I've got to put it in parentheses. So the CrO4 gets put in parentheses, and then the subscript gets put outside of it. Okay. So parentheses around polyatomic ions must be used only if you have to put a subscript on. If the subscript was 1, if we crisscross this, if we change this to sodium, which is +1, right? Then you wouldn't have to write the 1. You wouldn't have to use parentheses. Okay. Remember, 1s are redundant. You don't need to write them down. Okay. And then we already talked about the Roman numeral thing, right? Okay, the Roman numeral deal here. Oops, sorry, I forgot. This is why I have that note. My bad. Cu2O. What do we name this as? Okay. So let me erase this and clean this up one more time. So here's this formula, Cu2O, right? What are we going to name this as? Well, we know Cu is copper. We know O is, it's not oxygen, but it's oxide. Okay. But there's something missing here. If you look on your common ion sheet, right, you'll notice that copper, there's a couple of different kinds. There's copper 2 and there's copper 1, Roman numeral of 1 and copper 1, and Roman numeral of 2 and copper 2. Well, which is it? We got to determine that. Well, we got to understand here, this is oxide. Oxide has a -2 charge, okay? There are 2 copper ions in combination with it. So I'm just going to draw this out to prove a point, okay? So these 2 copper ions, remember the formula has to be, the charges need to offset, they need to equal 0. So that means that each one of these copper ions has to have a +1 charge. Okay, so the way this formula is written right here, this is copper 1 oxide. Okay. Now, this would be the formula for copper 2 oxide, CuO, copper 2 oxide. The oxide has a -2 charge. If there's only one copper atom in combination with it, that means it must be copper 2 with its +2 charge. Okay. So again, these are just a bunch of examples to kind of help set you guys up for working on the worksheet. Okay. Last couple options. So calcium oxide, it's right out. Calcium oxide. So calcium, this is, we kind of talked about this already, but Ca+2 oxide is -2. Okay. Use the old crisscross method, right? The charge becomes the subscript, absolute value subscript of the number. You know, you'd probably thinking it would be Ca2O2. Okay. But again, it needs to be an empirical formula. Can I simplify the ratio of 2 to 2? You bet. Okay. So it should be just CaO. So a little kind of rule to live by is that if I've got my 2 ions that I'm going to crisscross and smash together to form my formula for an ionic compound, if they are equal and opposite in charge already, just put the 2 elements together. CaO is the formula for calcium oxide. Okay. And then last example for today, and then I'm going to let you guys go, ammonium sulfide. Okay, so ammonium, remember that was Na, that's the only positive polyatomic ion that you guys will be held to knowing and using, ammonium, right? So, and then sulfide is S-2. Okay, sulfide is S-2. Okay. So crisscross method, boom, boom. Okay. If I'm going to put a subscript around the ammonium ion of 2, I've got to place parentheses around it. Do I need to write the subscript of 1 in the crisscross method for sulfur or the sulfide? No. Okay, so polyatomic ion, first position, kind of the one weirdo we got to look at. Okay, you got to put, if you're going to use a subscript other than 1, you got to put it in parentheses. Okay. All right. And then last thing, again, so remember we said, you know, one of the things that the keys here is that, like, if you look at, you know, all these formulas, so sodium chloride, magnesium sulfide, copper 1 oxide, you've got metals all over in the first position. Metals in the first position is like ding, ding, ding. This is an ionic compound. Ionic compounds behave a certain way. This allows us to differ, because later on, next, when we come back later after we get through the ions here, the ionic compounds, we're going to talk about naming and recognizing molecular compounds. They will possess all nonmetals. The one exception to this is the ammonium ion, right? If you see that NH4 sort of grouping in that first position in a formula or in a name for that matter, right? In a name for a compound, that ammonium is a polyatomic positive cation. It's the one weirdo. It's the one exception to this. Hey, look for a metal in the first position, like Mr. P said. And if there's a metal in the first position, we know it's an ionic compound, and we know we're going to name and identify it a certain way that we've taught you here today. Okay. And then, sorry, the last thing that I want to say to you guys before I sort of let you loose is, as you look at your common ion sheet, you'll notice like +1, +2, +3, -1, -2, -3. You remember back when we talked about this, right, on the periodic table. Group 1 elements have a tendency to be +1 ions. Why? Because they lose an electron to achieve an electron configuration of noble gas. Group 2 elements have a tendency to become +2 ions. You'll see all these +2 ions, magnesium, calcium, strontium, listed in that chart on the common ion sheet. Group 17 over here, they have a tendency to exist as -1 ions because they gain an electron. Group 16, -2 ions because they gain 2 electrons to achieve an electron configuration of a noble gas. Group 3, okay, nitride, phosphide, they gain 1, 2, 3 electrons to achieve an electron configuration of a noble gas. You'll see them listed like that on the common ion sheet. So position of the periodic table, charge tendency when these things exist as ions has to do with their electron configuration. All comes back to electrons and electron configurations. Okay. All right, guys. That is it. And you guys, I'm going to stop the video now. What you need to be doing is working on those practice problems, worksheets, naming and identifying ionic compounds. Your quiz will be exactly like this in a couple of days. I'm going to have either a formula and you're going to write down the name, or I'm going to have the name and you're going to write down the formula. For your homework, you guys need to be working on this worksheet. Tomorrow, we can answer any questions or ones that you guys have difficulty with and make sure that we're all on the same page to prep you for ultimately the quiz on naming ionic compounds. Thanks, guys. Thanks for putting up with this. Sorry I couldn't be there today, but I will see you guys hopefully tomorrow. Bye.